Hello everyone, welcome back to my channel. Today I'm going to talk about the particle swarm optimization, which is one of the meta-heuristic algorithm that was used in many real-world optimization problem, and it was used in many fields. It is a popular algorithm which was first introduced by Kennedy and Eberhart in 1995, and this is the paper from them. You can check this paper, and in this video we use the information from this paper as well, from Liang and Ching, about the comprehensive learning particle swarm optimizer in 2006. So I will leave the link of these two papers in the description, so please check it out, and don't forget to subscribe and hit the notification as well, so you won't miss the new video. And if you like this video, please put a thumb up. Okay, the idea of this video is that I'm going to apply the theory of the particle swarm optimization by using the Python code and solve the optimization problem. And in this case, I will solve the sphere function in this paper and compare the result. So this is the sphere function, and I will compare the result with the result from this literature, and also plot the result of the fitness value as well. So before I start, I want to talk briefly about the particle swarm optimization. So this algorithm is based on the behavior of a bird flock. You can see in this image all the particle in the search space try to search for the global optimum. It can be the global maximum or global minimum value of the objective function, but they need to update their position every iteration, as you can see here. So they need the velocity and the equation for update their position, and to do that, the algorithm proposed two equations. So we have the velocity equation represented by equation number 1 here, and the position equation represented by the equation number 2. So we have some parameter here, C1 and C2 will be equal to 2, and the ran 1 and ran 2 is the random number, random value within the range of 0 to 1, and P best is the personal best position, and G best is the global best position of each particle, and V is the velocity, X is the position, and we have also the W. It is the initial weight that vary from 0.9 to 0.4, and this is the velocity equation. So now I will start the Python code. So first thing first, I'm going to import a NumPy library and Matlab library as well, because we also need to plot the graph of the personal best, sorry, the global best fitness value of the objective function. So you can follow the flowchart in this paper, but first I want to define a function to calculate this value. So I'll call this square function, and input x. X is the numpy array, and what we do is we need to do the summation of the square x. So this will be square x, and then we return the result. So this is a square function. Okay, next we can follow the flowchart here. So first we start with the initial position and velocity, and then define the personal best position, personal best value, and also the global best position and global best value of the population as well. But before we start the algorithm, I want to define some value of the parameter of the algorithm. So this will be parameter setting, and the first thing is the dimension or variable of the function. It is equal to 10, and this value is from this paper, so please check this paper. I will follow everything in that paper. And next is the limit of the position, or the search space limit. The search space range of the function. So this will be equal to minus 100 and 100. And next one is the limit of velocity. And to define the limit of velocity, we can use the value from x min and x max, and normally it is equal to 20% of x max minus x min, and for the maximum value it is the positive value. And next we can set the maximum number of iteration. So I call this max it, and the value is 3000, and population size equal to 10, and the parameter c1 is equal to 2, and c2 is equal to 2 as well. Next one is the initial weight w, and as I mentioned, it is vary from 0.9 to 0.4 based on the number of the iteration. So you can use this formula. So this will start with 0 and maximum number of iteration, and maximum number of iteration. So what it means is the value w here will start with 0.9 at the first iteration, and end with the value 0.4 at the last iteration. Next we can start the algorithm. So we can look at the flowchart here. So I'm going to call this algorithm. And we start with defining a function. We call this optimization. And create a class. So the initial value will define in the part here. So you can use this style to make the code look a little bit more organized. So now I will start with the position. So the value of position is randomly created anywhere within the search space. So I'm going to use the command random from NumPy library, and the minimum value is xmin, and the maximum number will be 50. So we change this to 50, and for size of this matrix is the population size and dimension d. Next is the velocity. Again, this matrix the value of the velocity is randomly anywhere within the limit. So I will start with Vmin and Vmax. For the size is the same as the size of position. And next we can find the fitness value, and I'm going to call this cost. And for the size of this array is PS. PS is the population size. And to calculate the cost or the fitness value of the objective function, we need to call the square function that we created. So I'm going to set this cost equal to square, and import the value of position of each particle. So now you got the fitness value of the current position. Next, we can define the personal best position. So I'm going to call this P best, and I assume that the current position or the initial position that I just created is the personal best position. So I'm going to copy the value from the initial position, and for the P best cost, it is the personal best fitness value, also the same as the position cost, the initial position cost. So I use the command copy again, and cell cost. And next we need to find the value of a global best. So I need to create a variable index and find the minimum value of the personal best cost. So this command will return the index number of the minimum value in the personal best cost array, and we need this index in order to define the global best position. So now we call the value index, and again for the global best cost, we can find it by, this is a personal best cost, and we use the value index again. So now we got the personal best and the global best. Next we can create an array that collect all the data from every iteration. So I'm going to call this best cost and create a numpy array with the size of maximum number of iteration. So now we got the initial value. We can start the first iteration. So I need to define another function and call this evaluate. So the algorithm is start from the first iteration. So we need a loop function or a loop command that start from 0 to maximum number of iteration, and then we need another loop that start from the first population or the first particle to the last particle in the population. So this will be in range of PS, which is the number of population size. And then we can start find or update the velocity by using the equation, and also the position of each particle as well. So this will be velocity, and the formula will start with the initial weight and velocity, and we can now write another the second term here. Start with C1 random number 1 p best minus x. So this C1 multiplied by random number with rank 0 to 1, and the size of this number or the array here is the size d, because we have the dimension here with the value 10, and multiplied by p best position, personal best position, minus the current position. And now we need to add another term, C2 random value 2, and then multiply by global best minus current position. So this will be C2, and again random value with the size D, and multiply by G base minus self current position. So now we got the value of velocity. We can update the position. So this will be a position equal to self position itself and plus the velocity. So now we got the velocity and the position. Next we need to check that the velocity and position is within the search space or not. So first you can start by set the limit of the velocity. So I want to define the function that control the limit of velocity. So first we need a loop command. And if vi bigger than Vmax, the value vi will be equal to Vmax. And again it's the same for the minimum value. So now you can this is the v. So now you can call the function limit v in this line. So I'm going to set the velocity I equal to limit v and self velocity. And next we need to check the position as well. So I'm going to copy this. Sorry, I think this one need to return value, which is the array v, and this one also. So this is x, also x, and we can call the function again. Limit x, and this is position. So now we find the velocity and position. Next we can compare the fitness value of the particle to see if it is better than the previous value or not. And if it is the better than personal best, we need to compare that it is better than the global best value or not. So we need to call the square function again to find the fitness value. So this is the cost equal to square and cell position, so that it will call it will take the current position into the calculation. Next we can compare the cost or the fitness value. So in this problem we will find the minimum value, so this will be the smaller sign. If it is smaller than the personal best cost, we need to update the personal best position and also the personal best itself as well. So the personal best will equal to the current position, and also the personal best cost will equal to the current cost. And next we need to compare with the global best cost. And if this statement is true, we can set the global best position now is equal to the current position, which is equal to P best. And also the global best cost equal to the current cost. So now we complete the comparison. We can start collecting the data. So I will call the variable best cost that we create here, and this will be equal to G global best cost. So now the algorithm is complete. Next we can start by doing the plot of the graph of the global best fitness value for every iteration. So in order to plot the result and compare with this one, we need to use the command semi-log following the y-axis and use the value best cost. And next we can start running this code. So I need to call the function plot as well, and we need to call the function optimization. Now to show the value of the global best fitness value at the last iteration, we can print it here, and we call this best fitness value equal to cell global best cost. Now I can run this. So there there is an error, and we can check the line here, number 53. And okay, I think this one is not correct. Sorry. Okay. Okay, now we got the result here, and this is the graph. So this is the result, and you can compare this this result here with the result in literature, and this is the graph, and this is the result that we can compare. So the value is PSO. It is stand for the particle swarm optimization. You can check here. It actually better than the one in the literature, but you can see that the algorithm start to find the optimal result in this graph. So this is how you implement the theory of particle swarm optimization into the Python code programming language. And we can use this algorithm in many fields, in civil engineering also. In the next video, I will talk about the particle swarm optimization that we can apply to the optimization of the truss structure. So please keep checking my channel, and don't forget to subscribe and hit the notification as well. So thank you very much for watching. I'll see you guys in my next video.